Well, just a quick revision. So what we have done through the means of two different protocols, two different algorithms, is established the following theorem. So recall what we have shown is that a proportional allocation. So an allocation which is fair in the sense that everyone receives an interval, a connected piece of value at least 1 over n times the value for the entire resource, always exists. And furthermore, this can be computed efficiently even in this general Robertson Web query model. In this query model, where the sort of agents know their own values, and what you get to do is just query them, ask them, okay, how much do you value this interval? If you start here, where would you sort of cut to achieve a particular target value? So within these two eval and cut queries, we can sort of, with a polynomial number of queries, we can find proportional allocations that achieve proportionality. So valuation queries in the Robertson web model, which is again the very natural query model of interacting with agents through these two types of queries. And very specifically, like the moving knife procedure achieves this using n square queries. N again is the number of agents in my fair division exercise, and the second one we saw was this recursive algorithm by Even and Patch, and this required, in fact, 2n log n queries. So sort of something, the number of queries that's sort of proportional to the sorting thing. Okay, fine. As I said, what good is a theorem if you don't know 3 or more proofs of it? We have 2. There are others, something called like a last diminisher. There is in fact a randomized algorithm as well by Edmund and Proust. But the natural question now is that, okay, can we do better? Like, we kind of, with this nice recursive idea, we have gone down from n square queries, a quadratic number of queries, to notably a smaller query count, which is of n log n. Yeah, so like good engineers, like good computer scientists, natural question is, okay, can we do even better? As in, can we say find a proportional allocation, say in linear number of queries? And the answer is actually no. And this is no, again, provably so. So the way this is done is by establishing a lower bound. And I'll just give a proof sketch of this lower bound, but I'll mention the result in its entirety. This is by Edmund and Proust, and again the handbook of computational social choice, the reference that I had pointed out earlier, is a good place to sort of read the details of this result. And the theorem of Edmund and Proust says that if I look at any proportional So by a proportional procedure, I mean a protocol, an algorithm that finds a proportional fair division, finds a division where everyone receives an interval of value at least 1 over n. Then in the sort of Robertson web query model, in the query model that we've been looking at, then any such proportional protocol, procedure, algorithm needs omega n. Right, so effectively what this means is that the up to constants the even paths, the recursive method we saw is in fact provably optimal. You cannot develop a protocol, provably so, which outperforms this procedure in terms of the number of queries you need to find a proportional allocation. This is a very nice, tight matching lower bound. It's a day of celebration when you actually find a result where there's an algorithm and a matching lower bound. So certainly a rarity. It's sort of a tiger sighting of sorts. So something to sort of appreciate. Very quickly, the way this is done is so I hope everyone is sort of familiar with this omega notation, right? This just means so standard big O notation. Roughly speaking, this means that if you give me any algorithm asymptotically, if it finds a proportional fair division, then it will have to query like either cut queries or eval queries, and the total number of queries will be at least n log n, right, up to constants, which are sort of that hidden in this omega notation. Okay, so the proof is somewhat technical, though not very difficult, but the key, let me actually mention the key idea or sort of the key construct that goes into it. And the fact is that, again, this is a proof sketch. I'm not going to sort of go over through the entirety of it. But the key idea is that if you are finding a proportional so if you are finding an allocation, say I1 through In, where again the agent I receives interval II, then for a large number of agents, you would have actually found such an interval of small length, right? So note that if I give you one specific agent and ask you, okay, give me an interval. So I give you an agent A. I'm not concerned about other agents. And for this agent, I ask you, give me an interval such that this interval is of value at least 1 over n for this agent A. How can you blindly answer, give me back a response? So let me ask the question again. I fix an agent, one special agent. For this agent, I want an interval such that this interval is of value at least 1 over n for this fixed chosen agent A. My question to you is, how can you answer this question without much effort? What was that? Just return the whole cake, right? Trivial. You just, I mean, I fixed any. There's no concern for any other agent, right? If this is sort of a super entitled agent and you really don't want to worry about other agents, there's a very simple way to find an interval that satisfies this inequality. Just set IA to be the whole cake. The value is 1, you get it, fine. But note that what's sort of difficult in proportionality is you want to achieve it simultaneously, you want to achieve it for all agents. What this does impose upon you is the fact that for a large number of agents, the length of the interval that they obtain in, say, this proportional allocation will not be too large, right? So what I'm saying is that let's do this. Let's look at the length of an interval. So what is the length? It's just literally the length of I in particular. So say IA is x, it's an interval from x to y, the length of IA is y minus x. It's just the physical, it's this length of the interval. Now note that if I sum this up across all agents, what do I get? So I have my allocation, so this is I1 through In, again in some order, so agent 7 receives this, agent 4 receives this, so on and so forth. IA is somewhere. So these are the intervals assigned, disjoint intervals. So if I sum the lengths up of these intervals, what do I get? 1, right? It's just literally just summing up these lengths. So this is 1. So this effectively through an averaging argument that I'll detail in a second means that for so what I'm saying is that if I look at an allocation, in fact, it doesn't even have to be a proportional allocation. Just the fact that it is a partition of the cake means that for a large chunk of agents, for at least half of the agents, if I look at the length of the interval that they have received, that length cannot be more than 2 over n. Right, and the proof of this observation is simply by contradiction. Say this is not the case. There are more than n by 2 agents who receive an interval of length more than 2 by n, the sort of, I assume the opposite towards a contradiction, then so towards a contradiction, if n by 2 agents have sort of the length more than 2 by n, well, if you sum their intervals up, then that length, the sum of lengths would be just summing up these n by 2 agents would actually come up to be more than 1. There are n by 2 of them, each guy has 2 by n, multiply these two numbers out, what you get is something strictly more than 1. This cannot happen. Again, I'm writing down formally a sort of very obvious fact, which is that on average, I mean, a large number of people cannot be more than much higher than the average. Note that the average length here is actually 1 over n. The n people, their total is 1. So the average length is 1 over n. And this is sort of just an observation that follows out of it. If you want to sound fancy, this is what's called Markov's inequality. Right? So interpreted in a probabilistic context, this is nothing but that. But again, it's sort of a simple averaging thing that, like, if I look at the average height of individuals in this room, it cannot be that half of you are of height more than twice the average. Here's the proof. Very useful fact in many contexts. So fine. So let me kind of keep this out. So what it boils down to is that when you find a proportional allocation, you are not only ensuring that all the agents get a large value, you also ensure that you also, in the process, you also achieve the fact that the length of a bunch of these intervals is small for right. So again, I'm just erasing down the definition of length. I kind of hope this is the standard enough to keep in mind. So what this says is that, look, like it's not just finding high values. The another task at hand is to actually find this high values in fairly small length intervals. So that actually complicates things a bit. So again, individually, if I fix an agent and I ask you for an interval that achieves value 1 over n, it's a very simple task. Once I fix the agent, you can just tell me, okay, look at the whole cake. Obviously, that's one interval that achieves a value of 1 over n. At the same time, if I just focus at this property in isolation, so I give you an agent and I ask you, okay, give me a interval IA that is of length less than 2 by n, what can you do? So if I just wanted to find an interval with just the second property, how would I go about doing it? Well, I'll just pick any interval of length less than 2 over n, just the first one, from 0 to 2 over n. So, I mean, length is completely independent of value, you're good to go. So, in isolation, these two properties are easy to obtain. What's important to note here is that when you have a proportional allocation, you are achieving both of these two properties simultaneously, which is what kind of makes things difficult. You have to now know the valuation well enough such that you achieve this sort of proportional value of 1 over n in a small enough length. And this is what sort of makes the problem difficult. So, the term used in the proof of Edmund and proves is that these are what are called rich intervals that achieve a value of 1 over n. Intervals of length less than 2 over n are called thin intervals. That's the jargon they use. And the sort of key observation, again, not being too formal, is that so one has to find like rich and so in order to find a proportional allocation for a large number of agents, or at least half the agents, you will have to find an interval that's both rich, i.e. has a large value, and at the same time thin, right? And the point is that, so this implies that if I define Tn to be the time required to find such a rich and thin interval, the time to find a proportional allocation is sort of lower bounded, is at least n times Tn. So this omega is sort of hiding this factor of 1/2, but that's sort of the formal implication. Again, I'm being sort of not going over all the details, but one can argue this formally, that if Tn is the time required to find it for one specific agent, given the fact that the valuations of players are distinct, like knowing one agent's valuation tells you nothing about any other agent's valuation, means that if you have this Tn, you will need to spend this much amount of time to find a proportional allocation. This Tn gets multiplied by a factor of n. What this lets you do is sort of isolate the problem. Now you can look at one specific agent, because this problem of finding a rich thin interval is a agent specific problem. It's not a problem that requires all of the agents together. So with this Tn, what's shown, and something that I'm kind of omitting right now, is that this Tn itself is omega log n. You cannot achieve this for a very sort of structured family of valuation using less than log n queries. This is sort of a nice construction. It's a valuation that's sort of based on a particular tree that's imposed on the cake. So something that's sort of worth reading. But yeah, in the interest of keeping things simple, I'll not kind of go over it. But the point is that you kind of reduce the proportional to this problem of finding rich thin intervals, and actually you get a major advantage of n here. So this by itself gives you a omega n lower bound, which is not that interesting. But what you can show is that this, for any specific agent, when you have n agents, this is sort of finding thin rich is at least log n, right? So note that, like, though this is dependent on a single agent, the fact is that the thinness and the richness has a factor of n, and hence that kind of shows up as a log n here. Again, if there's interest in the sort of the tutorial section or one of these offline sessions, we can kind of go over it. What's notable about it is it's a standalone lower bound. It does not rely upon lower bounds on other problems. It sort of does not piggyback on other results. So it's a sort of fairly nice self-contained result. And for a specific agent. So it's a, yeah, so you fix an agent A and you say that an interval is rich for that. Thinness is again universal. So the problem, so fix an agent A, the problem of finding a thin rich agent is find an interval which is of this sort. I mean, note that, in some sense the idea is you have to do sort of a binary search over like roughly n by 2 intervals, and this is sort of where log n sort of comes in. I mean, that doesn't really translate into a formal proof. To obtain a formal proof, you have to construct valuation classes, but in the lower bound actually piggybacks on this problem, which is sort of nice in and of itself. So here's a good question, the answer to which I'm not, sort of open question to me, is that say I actually give you an algorithm that for agents finds thin rich intervals. So let's just, again, this is a exercise whose answer even I'm not completely sure of. So you have an algorithm that's given to you as a subroutine. You can feed an agent to this subroutine along with some interval, and the algorithm will return a thin rich interval, like a sub-interval of what you have given as the interval that you have passed it on, if one exists or says there isn't one. Now, using that as a subroutine, can you find a proportional allocation in exactly, like, using order n invocations to that algorithm? So that would be a nice converse connection, which I'm not sure is a sort of nice open question worth thinking about. Okay. So that kind of is the proof sketch I wanted to address regarding proportional divisions. This in particular, as I mentioned earlier, shows that the recursive algorithm that we have seen is in fact optimal. You cannot hope to design a method, a protocol that finds a proportional allocation within n log n number of, within order n log n number of queries. So with that, we are at the end of proportional cake divisions. Yeah, so if there's any solace, and if you think this was messy, what I can tell you is that NV freeness is even worse. It's there, like negative results abound, and indeed, like we have seen that NV freeness implies proportionality, so in that sense it's a likely a harder solution concept. It turns out it's a fairly elusive solution concept. It's this sort of the level of generality that we have enjoyed with proportional allocations does not sort of continue to carry on when working with NV-free solutions. Okay, so that's the length and breadth of what I wanted to talk about proportional allocations, fair division with respect to proportionality. I'll now move on to NV freeness. Okay, so again, so I'll say that an allocation is NV free if, again, obviously no one is envious, so every agent looks at the interval that's assigned to it, and this is of value at least IB for all agents in participating in the fair division exercise. So this is just a repeat of the definition. No one wants to swap, no one values someone else's interval more than their own. So now though, let's kind of relax it a bit and sort of consider like each IA to be sort of so we actually got a very nice property with proportional fair divisions, that is everyone got a connected piece. No one, like the cake, that part of the cake that you received wasn't like crumbed up and wasn't chopped, cut into finely, chopped into fine pieces. I mean, for like going ahead a bit, this sort of nice result is not possible in the case of NV freeness. I'll formally state what this means soon. So towards that end, let's relax it and consider a setup where I actually allow you to assign each agent a bunch of intervals, but a finite union of them. So what do I mean? I mean that, let's say I have the cake 0, 1. So now agent A can get this piece, this interval, and a third interval here. So again, the intervals that I assign to different agents are pairwise disjoint. I cannot like pick a piece and say, okay, it's going to both two players. But what I can now do is that look at a case where the single agent actually receives a union of intervals. So it's a finite union of intervals. So the scenario looks like this. Again, the subscript denotes the agent's index, the agent that receives these three. The superscript, say, denotes the sort of the index of the piece. So what could happen is that IB gets here, and then agent B also receives these two pieces. So this is how it is. So so in the case of proportionality, how many cuts did I make to find a fair division? So there are n agents. How many cuts did I need? What is that? 2 agents, how many cuts did I make? N minus 1, perfect, right. So n minus 1 gives you n pieces and you just shuffle them around. And now I'm saying, okay, fine, I'll make more than n minus 1, I'll kind of partition it and like shuffle. So you like this part and this part, you get these two, I like something in the middle, I'll get that, so on. So it's certainly a relaxation in the sense that I'm allowing more flexibility to you, fine. And the question is, okay, now can you do something interesting? Now can you find NV-free allocations? So let me start with the bad news first, and this is major bad news, right? It's like the Sensex falling of sorts. And the idea here is, so the first sort of the first negative result, which again is somewhat technical and will require some sort of constructs to be cleared, something called rigid measure systems, can be done, but yeah, it's sort of will be a bit intricate for the purposes of these lectures. So I'll just state the result, explain it, and happily move on for both of us. The first negative result is by Stromquist that actually shows that so the first one says, like, look, if you stick to allocations, if you stick to the requirement that every agent must get a single finite time, bounded time, yeah. So the first negative, strong negative result by Stromquist says that, look, if you want to stick to the requirement that every agent must get a connected piece, you're out of luck. Forget poly time, forget exponential time, forget n to the n to the n time. There isn't a finite time algorithm that will find it for you, right? It's a strong negative result, but it's in a model where it's in again the Robertson web query model, but it's sort of an adaptive adversary, which means that there's an adversary sitting behind who's answering these cut eval queries, the Robertson web queries that you ask, and he's kind of adversarial, he'll shift based on whatever you have asked so far. So it is in a strong model, a strong adversarial model, but still it's a drastically negative result, and like to sort of rub salt in the wound, this actually holds for n equal to 3. So why can't, or can I expect this can I expect to strengthen this result for n equal to 2? Can I work hard and achieve such a negative result for 2 agents? No. Why? The cut and choose protocol does it for me. Like for 2 agents, like the first thing we saw was NV free for 2 agents. So I already have a finite, forget finite, it's a 2 query. It's a 1 query thing. You just ask the first guy cut, ask the second guy the eval. So 2 or 3 queries, you're done. So for 2 agents, you essentially need 3 queries. For 3 agents, you need the unbounded number of queries. So in terms of jumps, it's a big one. It's a strong negative sweeping result, right? So, okay, sort of, I was kind of foreshadowing this for quite some time. Next question is fine, now that you have given us a relaxation where I can look at crumbs, assign agents a union, finite union of intervals, well, then what can you do? So it's not necessarily a negative result. Okay, it depends on what you call negative. I actually I like the result, so I'll not quantify it as negative. But for the second case of there's this nice result by Aziz and McKenzie. It's not too old. It's in fact result from 2016 that gives a finite time algorithm. But in terms of, it's very generous with the word finite. So it finds, so again, in this sort of non-contiguous model, because for the contiguous model we have this negative result, and both of these are in the Robertson web query model. So it finds an NV-free division using, okay, let's start n to the 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 n queries. Right, so it's a tower of n's, and I challenge you to give me another algorithm with this matching running time bound. Furthermore, I challenge you to explain this algorithm to me. Right, so it's certainly non-trivial. If you feel tired now, we can have an entire summer school dedicated to these results. It's a tower of 6 n's. Yeah, so this is a rarity, but yeah, it's up there. So that's the number of queries you'll need to find an NV-free allocation. Fine. You can say, okay, maybe the problem is genuinely difficult when you allow for, even when you allow for this relaxation. But here is where the community working on cake cutting needs to shy away and hang its head a bit. The lower bound for this is n square. Right, so again, lower bound not in this contiguous pieces setting, it's in the finite union, it's omega n square. However, which way you look at it, there is a large gap between these two. Right, try plugging in 3 and computing this tower of n. Probably by the end of this week you'll find that number. It's a large gap. It's like a starking, like it's a sort of blatant open problem facing us. But yeah, this is it's a challenging open problem as well. It's not obvious how to sort of bridge this gap. And again, this is sort of intuitive, but the idea is that like not too many connections are known between like lower bounds of these things versus lower bounds for other like more well-studied problems. So going back to the slow bound for proportionality, going back to the result of Edmond and Proust, the n log n one, well, there it was standalone. So it's actually nicer in some sense, again, from a sort of understanding perspective, if you connect problems, connect to things that you already know are hard. So that's in some sense lacking. This is what kind of a very rough, intuitive, high-level idea why there's a large gap between the lower bound and this upper bound. So it's a NV freeness. Again, the purpose of this slide is to convince you of the fact that if you want to find, if you go in a party with even 3 people, and you really want to find an NV-free cake cut, yeah, good luck. Yeah, this is, the party will end before this thing sort of runs to completion. What is that? It's again through like constructing families of valuations. It's similar. There's some work by Nissan and some, like it's again these sort of extension of these rigid measure systems and so on. So the lower bounds are sort of it's again constructing particular valuations and saying that for you have to query it enough times before something meaningful can be extracted. Yeah. Okay. Just to sort of impress, like state this fact again, all of this is in the Robertson web model. If you have piecewise constant valuations, things are better. You do obtain sort of better running time and better algorithms. So, okay, I have probably scared you enough about NV freeness, but let me sort of say that, look, interesting things can be done for at least a small number of cases. So if you have a small friend circle, 2 we have already seen. say you are very social and you actually have two friends, so there are 3 of you, then what can you do? So this sort of brings us to this protocol of right. Again, like if I were to present this result upfront, you would have said, okay, what's so great is telling me a solution for 3 agents, but probably after this tower of hyper exponential beast staring at you, this would actually convince you that something interesting is happening even for the n equal to 3 case. In fact, like there's a much fairly complicated algorithm for n equal to 4 as well. It uses something like 180, 190 queries, but yeah, like trying to explain that is a challenge in itself. But this is again sort of a classic algorithm by Selfridge and Conway. This is going to be for non-contiguous pieces, and it's again going to be in the Robertson web query model. That is, you can run this protocol just by pinging the agents, asking them for their values, asking them to make cuts of at particular points. Okay, so the protocol has 3 stages. Let's go over them one after the other. So again, I want to find a partition of the cake, now not necessarily into 3 intervals, more than 3 intervals, such that if I give particular unions of intervals to individuals, I achieve NV freeness. So it is in that setting. So what I'll do first is I'll ask, so I have 3 agents. So I'll ask the first agent to I'll go to the first agent and I'll ask this agent, okay, can you please cut the cake into 3 intervals, so make 2 cuts such that your value for all of these 3 intervals is exactly equal to 1/3. For you, all of these 3 intervals are of equal value. So how many queries do I need to actually accomplish this in our Robertson web query model? How will I very specifically execute this in the Robertson web query model? What is that? Yeah, exactly. So what you'll do is this is the cake, and you want to find for ask agent 1. So first query him with a cut query. So what you'll do is something like you'll call agent 1. You'll say, okay, starting at 0, can you find me a cut such that the value that you obtain is 1/3. So recall that in the cut query, this is the target value. So this returns, say, some point x. Right, so this is the response of the first agent. It's this point x such that this value is equal to 1/3. Right, so value 1 from 0 to x is exactly equal to 1/3. And then you'll again repeat it with another cut query starting at x. So then you'll say cut if I start with this x, the one that you have returned, again 1, 3. So I want you to find me another point y such that this value for 1, x, y, this interval is 1/3. Since the valuations are additive, this is 1/3, this is 1/3, the third piece is also 1/3. For, I mean, it's sort of a natural idea. What you have done is, you have said, okay, partition it into 3 parts, such that you are indifferent between the 3. In particular, this ensures that if the first agent receives any one of these 3 pieces and the other 2 agents sort of go to the other 2 pieces, you are done. Right. So this is very analogous to the cut and choose where Abraham, the first agent, was splitting it half and half. I'm now doing it 1/3, 1/3, 1/3. In particular, if we allocate these 3 intervals in any which way, the first agent, the one that has made these cuts, will be NV free. She is indifferent between the 3 pieces, right? So that's sort of the natural first phase, first stage of this protocol. So now comes the sort of interesting part. Yeah, it's a mouthful, I'll just explain it in a second. So, okay. So these x and y are marked by the first agent. I'm done with the first agent. Now I move on to the second agent, and I'll ask the second agent, okay, you know what? Tell me which is the 2 most valued pieces among these 3 for you. So now I'm asking this to the second agent. I'm now doing this exercise with respect to the valuation of the second agent. So again, up to sort of indexing and so on. So I mean, this shuffles can happen, but let's say that x1, this the leftmost interval, is the most valued interval for agent 2. Again, let me emphasize, this indexing is not an assignment yet. So if you want, I can sort of make it a superscript. So I have 3 pieces for 3 intervals. For agent 1, they are all equivalued, but I have indexed them such that agent 2 values x1 more than x2 and agent 2 values x2 more than x3. Right. So again, where they are located doesn't matter. It can be that this is x2 and this is x1, by which I mean the middle piece is the most valued piece by the second agent and the leftmost piece is the second largest, and so on. Fine. So let's look at a very nice case which might happen, might not happen, but if it does, like it's a special case, it sort of illuminates what's coming up next. Say, magically, for some reason, what ends up happening is that for the second agent, the largest 2 pieces with respect to its own value are equal. That is, I'm saying, again, this is sort of a assumption that's certainly not going to hold in general, but I'm just making it to sort of explain the algorithm. So assume that for the second agent, the value of the most, so I know that this is at least the value of x2, but say it just so happens that this is equal. Right. Asking all 3 to be equal will be a bit too much, but let's say you don't go that far, just go one step and say that for the second agent, so the largest 2 pieces are of, largest in the sense of V2's value, are of the same value. My point now is that if this were to happen, I'm actually good to go. Why is that? Fine. Let's be a bit more specific. Which one do you give to the third agent? You're almost there. It's just one idea that, what is that? Why x3? So, yeah, there's a choose point that I want to like tease out. What does 3 get? Why almost there? Like why can't third choose among all 3? So I want to, let's say I want to ensure NV freeness for x3, right? Somehow I am like the stars have aligned that I'll be able to manage it for x1 and x2. So forget about x1 and like sorry have aligned. So I'll be happy for agent 1 and 2. Agent 3 hasn't made an appearance yet, so I have no idea about its value. My observation here is that let agent 3 walk in and like a boss pick among all these 3, right? Why is it the case that agent 3 will be NV free if I actually do this? It's getting the best of the world, right? It's just walking in and saying, okay, I want this, so obviously whatever choice x3 makes, it will be NV free. It's got to go first, and it's like the birthday boy walking in, picking the cake it liked, piece of the cake it liked. Excellent. Now my point is that using this property I can actually argue that agent 2, so I'm now going in reverse order, agent 1 made the cut, agent 2 had this property, now agent 3 actually were to pick it. My claim is that if this were to hold true, agent 2 will also achieve NV freeness. Why? So there are 2 pieces that are of equal value and they are say greater than the third thing. That's sort of the indexing that's been induced by V2. The observation is quite simple. Look, either the third agent picked x1 or it picks x2. One of the 2, fine. Agent 2 now comes in and picks whatever is left. These 2 are more than the third piece, and it simply values these 2 equally. So agent 2 will end up being NV free. It doesn't matter what, agent 2 had 2 choices, right? So both of them can't be would not have been gone by now because only one piece has been selected by 3. So 2 comes in, picks off x1 and x2, whichever is left. Agent 3 is like the most accommodating guy in the world. He's the one who has made 3 equipartition. He's like, okay, it doesn't matter whatever is left. I was happy on day 1, I'm still happy. Doesn't give me anything, I'll walk satisfied, I'll walk away NV free. Fine. So what this tells me is that, okay, if I were to do the following, that if this case happened, then that will effectively lead me to an NV free allocation. In fact, it will lead me to an NV free allocation where everyone gets an interval, right? So, but this is something strong and might hold, might not hold. So with this explanation, let's kind of try to mimic it, and the way we mimic it is exactly through this step. The step says, look, I ask agent 2, and now it is the case that I have a strict inequality. So with respect to agent 2, this piece that I have indexed exactly to follow this inequality has this sequence. That is, with respect to agent 2, x1 is the highest valued piece, x2 is the second highest valued piece, x3 is the third highest valued piece. So what I'll do is ask agent 2, okay, trim something away. So find a chunk here, say x prime, such that once I remove it, I actually fall back into the nice case that I have. So this second step, which I have written in so many words, essentially means that I find x prime such that once I remove x prime from the largest valued piece with respect to V2, this is equal to V2x. So I force this equality by like trimming away a piece. Again, almost Pavlovian. How do I do this in the Robertson web query model? Yes. Perfect. Subtract the value to get x prime. It's additive, so again, a simple idea, you find the value of x2, you find this side, then you find value of x1. Look at the difference. Starting from this endpoint, you call cut to, with that difference value, you'll get exactly the cut here, which means that this part that remains, which is x1 minus x prime, will satisfy this equality courtesy additivity of valuations. Boom. Okay, let's stop again and see like are we making progress. So let's say, and again this is a hypothetical assumption, solely a thought experiment for the purposes of explanation. Say I can throw some cake away, right? I do not buy into the green initiative of IIT Gandhinagar. I'm happy to throw things out, and I'm happy to throw x prime away. My claim to you is that again we are done. I will be able to find an NV-free allocation. Why? Right, you just throw x prime away and run the previous idea. Right. Though note that if I am allowed to throw things away, there is a very trivial NV-free allocation, which is what? Just throw the whole cake away. Right. You guys have like, yeah, valuations are distinct, fighting like n to the n to the n. Here you go. Everyone gets a big empty set. Have to be NV free, right? It's a shared misery. So in that sense, not a very sort of grand idea by itself. Something called free disposal, and again, if time permits, we'll kind of circle back to it. That in certain cases, okay, we can sort of suffer some of this. But for the time being, the idea is you kind of find x prime, make these equal, and sort of reduce to the nice case that you had. And in particular, what you do is you now look at two cakes. So I have cake 1, which is which is this trimmed thing, and I have cake 2, which is the sort of trimmed part. So I'll run like now into the remaining two stages. What I'll do is find NV-free divisions of these two things individually. You might wonder that, look, I mean, okay, what you have done is sort of, this first cake is kind of nice. We have seen why, like, if we sort of allow first agent 3, then agent 2, and then agent 1, then why this would necessarily lead to an NV-free. But cake 2, like, okay, you have just probably just reduced the problem as is. But note that cake 2 has a nice property that its value is sort of low enough for agent 1. So just hold that thought, and I'll kind of now argue that why, I'll soon argue why I can sort of accomplish NV freeness even with this sort of trimming in hand. So, okay, so these are my two cakes, and let me get to so stage 1 is addresses cake 1, and it's pretty much the kind of observation that we had made, which is that sort of player 3 chooses first. And I mean, at this point, it makes sense, right? Like this is, right, the two equivalent pieces for the second player. So let the third player pick something, like player 2 picks next with. So what do I mean by x1 minus x prime as default? So I have this cake division, and agent 3 walks in and then picks the best of the one. Like again, the boss has come in, picks any of the three. So if player 3 ends up picking this x1 minus x prime, the trimmed piece, let it be, then player 2 can go ahead and pick x2, fine. But if player 3 does not pick the trimmed piece, I am actually forcing player 2 to pick it. So you have trimmed it, which means that you have this inequality, so you better pick the trimmed piece. What I am explicitly enforcing through this is that agent 1 doesn't land up with the trimmed piece. Right? So that's something that I'm, like this default option explicitly removes. And the reason is quite natural. What I'm saying here is that, look, player 1 has actually marked x1 as a whole. It's not good to give something smaller. So this trim piece should not go to player 1, which is exactly being sort of ruled away by this default choice. And player 2 is not unhappy with this trim piece. In fact, it's a largest valued piece for it. Okay. And then so it's poor board work, but I really don't want to move to a new page. Okay, so stage 1 is the division of the trimmed cake. We have painfully argued that this will lead to a division which is NV free. So if I stop now and not worry about x prime, I'm golden. Like what will end up happening is in fact an NV free allocation. Okay, but note that I still have to do x prime. And here's sort of the crucial observation which will guide you to design x prime. The fact that if I look at the player that has picked up the sort of trimmed piece, i.e. picked up this thing, will never be the source of NV for player 1. Right. In particular, even if, so there are two options, right? Either player 3 picks this trimmed piece or player 2 picks this. Right, and because player 2 by default will pick it. So between these two players, let's call, say T is the agent. I keep interchanging player and agent. I hope that's not a cause of confusion. This is. So it's sort of a delicate, I mean, it's an orchestra of an algorithm with 3 instruments playing. So you have to sort of appreciate the tones and overnotes, but it's sort of almost a very direct, yeah, yes, please. No, after so stage 1 is for cake 1. So stage 0 is I actually find this 2 cakes, looking only at agent 1 and agent 2. I keep this trimming aside, I hide it in some other room. I bring these 3 pieces in front of player 3, who gets to pick first. Whatever is left, the 2 pieces among those, player 2 picks, agent 2 picks, and finally player 1. So x prime, so it's post this trimming. Well, the preference, what do you mean sets his preferences? Yes. Yes. No, so like agent 3 walks in, look, he has only 3 options. Pick from, so this partition has been made. So it's being forced upon agent 3. So to be very specific, you call eval queries for all these 3 pieces in cake 1. And you pick the one wherein the eval return the highest number. Eval 3 of x1 minus x prime, eval 3 of x2, eval 3 of x3, pick the largest. That's what player 3 picks. If it picks the first one, kosher. If not, then player 2 is sort of the fallback option. Is that clear? Okay, let's circle back and note that one of these 2 gentlemen will have to, by sort of design, pick this trim piece. Whoever picks it, I'll call this person T. Again, a notational thing. Why am I doing this? Again, this T actually can go before agent 1 without ever causing any envy. Note that even if this agent T gets all of the second cake, agent 1 will not envy this guy. Right. So it's now when I'm doing the cake division for the x prime, it's in my best interest to let this agent T go first. So T again can be 2 or 3, but so I have 2 agents, 2 or 3, one of them picks the trimmed one, I'll call him T, and the other guy I'll call him T prime. This is sort of, yes. We are dealing with cake 2, yes. This is just this is a shorthand. I'm saying I look at stage 1. There's some person who has picked the trimmed piece, x1 minus x prime. I'll call him T, right? So again, the other way would have been like invoke it for 2. This is just two possible cases. So this is just naming. This is nomenclature. Just to ensure that T actually, whoever this T is, goes before 1. And that's kosher because even if this person goes before 1 and takes all of x prime, right? Note that agent 1 will not envy this person. Because this is x1 minus x prime. If T picks all of x prime, even then agent 1 will be like, you know what, this is still x1, which I don't. So note that agent 1 will get either x2 or x3 in stage 1, right, because of the design. So because it's indifferent, it's good to go. Fine. Yes? No? Okay. So the choice of T is explicitly to force the agent T to go first. Now what I'll do is this sort of ordering, the choose and cut and choose ordering is very suggestive. It says that whoever cuts should actually go at the end. Right, here player 1 was in charge of cutting the cake and can go at the end without creating envy. I'll repeat this idea. So here in stage 2, T prime, so cuts x prime, the trim. So stage 2 is dedicated to cake 2, cuts in sort of 3. Okay, so let's sort of zoom in on stage 2 and argue that this also will sort of ensure envy freeness. And this is again kind of, so note that T bar is the guy that actually did not get the trimmed piece. T is the guy that got this trimmed piece in the first stage. And so when T bar has cut these 3 pieces equally, it can go at the end, right? These guys can pick whatever they want. And it's indifferent between the 3 pieces of x prime. So T prime going at the end here for cake 2 is perfectly fine. T can go up ahead, and the key point again, which I've been sort of belaboring, is that this guy going before agent 1 will not create NV for agent 1 because of the fact that T has this thing. So even if in this case it would have selected the whole cake, agent 1 would not have been envious of it, right? Agent 1 has either x2 or x3, which is so indifferent to x1. So T with this trimmed plus even the whole trimmed thing will not be a source of envy for agent 1, yada yada yada. So again, I've kind of said it multiple times, but let me summarize. The idea is that if I look at the two stages in isolation, they are going to be envy free. Furthermore, the design, the fact that T goes before 1 ensures that envy freeness is maintained. So let me, yeah, it's difficult to, okay, let me try to, so let's do it like case by case for all three agents. So I have, so the first thing I'll want to argue is that agent 1 is not envious of anyone else. This is certainly true in the first stage, right? So in stage 1, this guy was getting either x2 or x3, right? This was by default going to player 2 that went before player 1. So again, not in stage 1, if I only look at cake 1, agent 1 is not envious. Fine. And this is also true, and this is sort of the whole so reason for doing this shenanigan of T and T prime, is that this is also true in stage 2, right? T was the guy that got the trimmed piece, even if it doesn't matter what it selects is a subset of x prime. So at the end, T will have this x1 minus x prime sum plus some chunk of x prime, which will not be of value more than x2 or x3, one of which has been given to agent 1. So this is completely golden for agent 1. Yes. Of T. Yeah. But you have to sort of argue it for T bar, which is also fine because T bar was actually going after agent 1. Yeah. Yeah, so you'll never envy someone who gets to select a piece after you, right? There were two pieces left. After T has selected a piece, two of them left. You actually pick the better one. So you'll not be envious. And now you sum the values up, you'll not be envious. So you're kind of golden with respect to T bar as well. Okay. Agent 2, again, note that in the first case, the equivalued argument, and in the second case, you have to do a case analysis of if it's T, fine, you're actually going first. So you're certainly not envious of people who are behind you in the queue. If it's T bar, then you have made it sort of equivalued and so on. So this is I've given you enough to sort of, you're paying attention for it even like 50% of the time, or half the part of the cake you would have, you can fill this up. Sort of, it's pretty much a case analysis of whoever is T prime. So two complementary cases, the thing unravels. Yeah, the sort of, to my mind, the interesting part is this trimming idea and then sort of ordering it, the cut and choose with the right imposition of this T and T bar. So that if you kind of appreciate that, you can sort of pretty much rederive the whole, or at least prove this case analysis quite as much. Okay, so this is for n equal to 3. Imagine what happens for n equal to 4, and imagine what happens for the towers of n. Again, thankfully for the both of us, we will stop here in terms of exact NV freeness. What I would want to now do, and this is again something like the one of the comments that we sort of made starting on, is that approximation actually is quite a powerful tool. Like, having seen this for n equal to 3, I'll actually describe a relatively and arguably much simpler algorithm that achieves approximate NV freeness, and it achieves it with contiguous pieces, right? So okay, what do I mean by approximate NV freeness? What I mean is that I will find, so efficiently, again efficiently in the my favorite Robertson web query model, and arguably by a fairly simple algorithm. So an allocation, and again when I say allocation, now I'm back to my more sort of restrictive, the more stringent requirement that I'll find these intervals. So every agent gets one unique interval, contiguous connected piece of the cake. Uh, so again, agent A gets interval IA. So what now happens is that if agent looks at its own value, this is at least some alpha times the value agent A has for some other interval, right? So when I plug in alpha equal to 1, I get back the standard NV freeness guarantee. This is exactly what Stromquist has ruled out. But now I'm kind of relaxing my objective. I'm saying, you know what, fine, I might not be able to achieve completely satisfy you, but I'll satisfy you to an extent, right? Again, what's the trivial case in this range? Something that, what is that? 1 by 0. Alright, it's saying I'll give you something that's of value 0. If I set alpha as 0, again, even I can design a simple algorithm for it. I don't even have to, 0 queries in the Robertson web model. Here you go, you get an empty set. Fine. But what we'll do is, like, we'll prove this result, we'll actually kind of come up with an algorithm that achieves this for a value of 1 over 3. Right, so this is the specific result I want to talk about. I'll give you an algorithm, arguably a fairly simple algorithm that finds an allocation where everyone values its own piece at least 1/3 times the value you have for any other interval. So it's an approximate NV freeness guarantee, but fine, it's still a non-trivial, it's still an interesting guarantee if you kind of squint hard enough. Okay. So I'll kind of not, in the interest of time, not write down the entire steps of the pseudocode. It's, if you have appreciated moving knives idea, this will sort of resonate a bit. So but let me kind of sketch the main points of the algorithm. So the idea is I'll initialize like a partial allocation, by which I mean I'll give every agent an interval. So again, these PIs, they are pairwise disjoint intervals, and I'll successively update them so that the values of the agent keeps on increasing. So if you look at the snapshot of an algorithm at some point, it will look like this. So some agent A has some interval here. There will be an unallocated chunk. Then there's some other agent B that has some part here, so on and so forth. So the idea is that I will sort of work with assigning intervals, disjoint intervals, but for the time being I've relinquished the during the execution of the algorithm, it's not necessary that I would have allocated the entire cake. So there will be parts that are unassigned as the algorithm sort of progresses. At the end, I'll actually sort of merge things to give you a genuine allocation. I'll give you intervals that are disjoint and whose union covers the whole cake. So there are n intervals. So how many unassigned intervals can there be? I give you the segment and I'm giving you n disjoint intervals on it. Might cover the whole cake, might not cover the whole cake, but how many unassigned intervals will be induced? What is that? At most n plus 1, right? There's a, like you just start like v1, then you have u2, yada yada yada, un plus 1. Right? There will be at most n plus 1 of them. Like plug in n intervals, you'll create n plus 1, at most n plus 1 voids. If these two PIs actually touch, then you'll have less, but again, at most n plus 1 of these unassigned intervals. So that's sort of a snapshot of the algorithm as it progresses. But let me be a bit more specific and tell you what the detailed steps are. So I'll initialize this as just the empty set. Right, I have to start somewhere. I give every guy an empty interval. So how many unassigned intervals are there at the beginning? 1, the giant whole thing. I haven't assigned anything. The whole cake is unassigned. So I will use this notation. The script P is this collection and UT is the sort of collection . So this is all the unassigned intervals, at most n plus 1 of them, that are induced if I look at a partial allocation of the cake. If I look at n intervals that are, again, the indexing is that PA goes to agent A, so on and so forth. So the idea is quite simple. I have a loop. So I look at the current state of things. There is some parts of the cake are assigned, some parts are unassigned. So I'm saying, okay, I'll keep on iterating, I'll keep on running this algorithm while the following condition is satisfied. That is, there is an agent A such that, so this, again, the superscript here is a timestamp. So P0 is the P superscript 0 means the initial partial allocation, and it's just the iteration count, if you will. So while this happens, that so this guy, agent A, looks at the current interval that's been given to it and says that, you know what, my value is in fact not only less than this piece of cake that's left on the table, but it's in fact less by a little margin. The rationale for the margin will become clear towards the end. It's just to sort of make progress every time. So in particular, this means that if A were to relinquish this piece PA, like the one that's currently assigned to it, and move to this U hat, its value will actually jump up by 1 over n square. Right, that's what it says. Note that I'm not making physical cuts. This is all like I'm just keeping this as for accounting. I'll find the final cuts only towards the end of the algorithm. This is sort of a thought experiment, right? So the player 1 is sort of committed to being given this. The cut hasn't been made, but at that point, player 1 comes and says, "Oh, hold on. What I'm getting is actually there's an unassigned piece. No one has claimed it, but that thing is actually of value, like a bit with a margin of 1 square more, 1 over n square more than what I have." The key point here is that if I do this switch, that is PA relinquishes this piece, that is this piece PT of A becomes unassigned and goes here, that again will continue to be a partial allocation. Right, that even if I assign all of U hat to PA, there'll still be no intersection explicitly because of the fact that U hat is an unassigned piece. So I'll keep iterating while this happens. Furthermore, so what I'll do is exactly what moving knife does. I'll start from X, keep moving a knife and cut it. The first point of time, an agent claims that the cut is of value 1 over n square more than its current thing. So what I'm saying is that, okay, this is U hat, this is X, this is Y. A bunch of agents satisfy this thing, not just A, there might be other contenders. I'll ask all of them to make cuts like RA, RB, RC, and these cuts are made such that if VC, say this Cth agent looks at X comma RC, then this is of value right. So I look at all agents that satisfy this, not just A but other agents for whom the U hat is of large enough value, and among them I ask for exact equality with again a margin, slight margin but a margin. So now I do the natural thing. So moving knife idea, I kind of move this way and I pick the person that has the leftmost mark and assign this to the agent. So I update the iteration count. So PT plus 1 of A hat becomes X RA hat. Note that this has increased the value of A hat by 1 over n square, and for every other agent things remain as such. That's it. That's my algorithm. Right. So I look at unassigned pieces of large value. I find the leftmost happy person first via moving knife. I do this allocation, update the iteration count, and I sort of continue on. So I mean, if you want, this is okay. So that's my idea. The loop will terminate when this condition fails. That is, for every agent, the currently allocated thing is of value more than like at least 1 minus n square all the unassigned pieces. Okay. So very sort of obvious fact that I will never assign intersecting pieces to agents, right? I'm always assigning, I'm looking at U hat, an unassigned piece, and I'm kind of moving on. Note that here, the piece that A hat had, like this PT of A hat, is now back in the pool, it becomes unassigned. So ut will be, ut plus 1 would be the new collection of unassigned pieces. So that's just a simple observation. Oh, so it's the leftmost mark such that so I mean you're doing this for every agent, right? You ask the agent through a sort of cut query, find me a cut point such that if I start at x, which is the left endpoint of u hat, the unassigned interval, this is of value, your current value plus this margin. U hat is an unassigned interval, yeah. So U hat is an unassigned interval. I can assign it without like creating any conflict. It's not, but if there is one such unassigned interval among the at most n minus 1 of them, you kind of do this. Okay, so you have, say, something like there's an unassigned interval 1, there's a assigned guy PA, there's a unassigned interval U2, then this is PB and so on. So this PA and PB are assigned. You look at U1 and see if there is an agent that values it more than its current value plus 1 over n square. If that's the case, you do this. Otherwise, you go on to U2 and so on. So you do this for one of these UIs. So U hat is one of these specific contiguous intervals. Does that make sense? Or?
So then x was bias in that figure, x was where it sees PB.
Yeah.
PB
Maybe, I mean here, so if I pick U2, this is x and this is y. It's the contiguous piece of, it's an interval that's completely unassigned.
And this U2 has got value
Uh,
greater than PA plus 1 by n square.
Yeah, so this is the current value of C, and this unassigned interval totally has value, I mean this inequality with 1 over n square moved here. So this says that, so if I look at, say U2 is the one that gets instantiated as U hat. So what this says is that A values U2 more than A values its current partial allocation plus. So it's not just more, it's more by a margin. So now with this as x, with this as y, you ask A, okay, give me a point such that this becomes equality. So it's exactly equal to 1 plus. So this might be more than this by a huge margin. I don't want to jump up that ahead, I'll give you more, but only a little. So, but now for U2, you look at all guys that are in the running for U2, which means this. And among all the contending guys, you pick the one who has the leftmost margin. Exactly like moving knife. Moving knife, where you shout out when the knife so you start at x, which is the left point of x2, and the first person to shout that now the piece between x and the current knife position is more than my current value plus 1 over n square. Yes? It very much so. Very, very much so. I haven't completed the algorithm description. If it isn't, then I have a nicer result, but it will be. And there's a reason I kept bugging you that how many, like counting that n plus 1 was a conscious, directed question. Right, but okay, what ends up happening is that at the end you have, say this is given to PC, this is given to PB, PA gets here, and they're unassigned intervals U1, U2, U3, U4, and so on. So when the algorithm terminates, for any agent, the value that it has for the PA that's assigned to it, the piece, is no less than like 1 over 1 minus 1 over n square of any unassigned piece, right? So So this is say P2, I've dropped like it terminates after say capital T steps. Right, so capital T is the number of times the loop goes, the number of times small t updates. So when you terminate, what you have is, so for all these unassigned intervals, you will have this property for all j and for all agents. Right, why is that? Well, if this wasn't the case, you would have continued on with the algorithm, right? It would have looped another time. Okay. So, but you're right, at this point I don't have a complete allocation of the cake, I only have a partial allocation. But what is interesting to note is that again, this selection rule, the idea that I give it to the leftmost guy ensures this property. It means that, look, I have given it, so if while I was doing an update, so this was u hat, it started at x, it's an unassigned interval, and I stopped at the first point where someone sort of raised hand and claimed this piece. Every other guy, the mark was to the right. Again, ties are broken arbitrarily, but this means is that this value for A, so say C was the person who sort of called out the moving knife, for A this thing, right, this interval was of value VA PT of A plus 1 over n square. But this is a subinterval of XRA, right? You have given a smaller chunk, you have given it to the guy who has claimed the smallest piece possible. So this is in fact greater than VA, so this is, note that PT plus 1 of C, the new piece. So this continues to hold. So again, taking 1 over n square on the right hand side, for A, the PT plus 1 of A is in fact the same as this, the allocation remained unchanged. I inductively maintain this property. Okay, let's just stare at it, right? So if I remove this additive term of 1 over n square, what I have is actually NV freeness. I have not assigned the whole part of the cake, so there is one step of the algorithm that still remains. But note that this is very close to what I want. Up to this small factor of 1 over n square, we are almost there. We are sort of, we have achieved NV freeness. Just squint away and ignore this additive term. This is exactly NV freeness. Very nice. Okay. Looking at this picture, can someone tell me how do I find an allocation out of it? And I will be a happy person. Yes. This is true for all A and B. For C, I mean, it continues to hold. C was, everyone else, the piece remained. C now is a higher valued piece, higher by a margin of 1 over n square. Yeah, so for C as well, this continues to hold. It's an important point, but yeah, sort of, C is happier now than before. Everyone else, the status quo is maintained. That's a very simple idea. I mean, in fact, throughout the day, I haven't asked you a single mathematically challenging question. This is perfectly in line with it. Just a cute sort of idea, has nothing to do with prior training, to be sort of frank. How do I get an allocation, like an interval assignment out of this, and sort of such that this boxed guarantee kind of continues to hold within some factor. Okay, let me, in the interest of time, sort of divulge the secret. You do the most natural thing, you just assign intervals that are coalesce them. So these three things, you just associate every unassigned interval with a PA that's right next to it, right? They are interlaced. A PA, there's a partial PA, there's an unassigned, there's a PB, there's an unassigned, yada yada yada. There are n plus 1 of them. So what you do is that this becomes IC. You look at the index here and make it IC with something added on. Okay, you are getting something more. Valuations are non-negative. You shouldn't be less happy. Furthermore, so this becomes IB, these three things joined, glued together. Again, this is an interval. They are contiguous. They are the intervals that are sort of adjacent. So this becomes IA, yada yada yada. Right. So before I move on, the first observation I want to make, and I'm hoping one of you will quickly answer it, is that the algorithm will not run for more than n cube iterations. Why? So it's a polytime algorithm. Why is that? Sooner you answer me, the sooner you'll get to go for a coffee break, if that's an incentive. Perfect. So every time you do this update, the utility of the agent, whoever that is, goes up by 1 over n square. Right? So for any agent, this cannot happen more than n squared times. The utility would go above 1, which is the normalization factor. So every agent gets called upon as A hat, the one that gets an update at most n squared times. There are n agents, you have an upper bound of n cube. Voila. Simple idea. Again, nothing sort of profound. Finally, why do I have a good approximation guarantee? Well, let's go to the next page and use this. So what I have is that this is PB, and there were two intervals, U and U prime next to it. How did I come up with IB? I would have, the most that I could have done was joined both of these two with PB. So right, so this is IB. That's the final allocation that the algorithm returns. Note that not only do I have this, I actually have this inequality with respect to U. Why do I have this? Well, the algorithm terminated with exactly when, like, this was satisfied for all A and for all U prime. Otherwise, you would have run this for one more time. And you not only have this, you have for the other unassigned interval that's sitting next to PB. So this is IB is these three intervals. Okay, I just sum them up. Note that IA, so IA is sitting some PB, like PT of A is sitting somewhere. The way IA was at least this much, right? It might have actually taken with it one of the sort of one or two of the adjacent intervals, but IA is at least this partial allocation. So 3 times VA of the returned allocation IA is at least this much. This is just monotonicity. Again, additivity of valuations. This is VA. These three things together constitute IB, right? P. This is like stitching together these three things. So what you get is that, again, just So my claim to you is that this is a second order term. I can ignore it. In particular, I can argue that this thing is at least going to be 1 over, close to 1 over 2n, at least 1 over 2n minus some small factor. So this essentially translates into there's a small fudge factor in the denominator, but I'm saying that this thing is large enough that you can eat it on the left hand side. It's a 1 over 3 approximation. Okay, I spent almost the entire lecture on a n equal to 3 case and managed to give you an approximation in almost 1/3 its time. Okay, arguably a 1/3 approximation, but a fairly generic result for any number of agents. Polytime runs in Robertson web query model, good approximation guarantee. I will leave it as an exercise for you to sort of translate this additive factor into a purely multiplicative one, but I'll stop here, and any questions I'll be happy to answer them now. Again, do appreciate the fact that I still haven't given you a proof of existence of general NV free allocations. So that's coming, you can't sort of escape that, but that will involve arguably a sophisticated mathematical tool, but this is completely elementary. I'm just averaging, I'm sort of like literally sticking things together, and just, yeah, a patient like high schooler should be able to run through this algorithm. Nothing, not even a named inequality has been invoked. So a very simple algorithm leads you to a 1/3 approximation guarantee. So again, not the sort of power of approximation sort of shines here. That's sort of the fact to note, if nothing else.